So I think these were the 4 abstractions we have derived from the previous class after relating all the variables, and this should be handy for us to solve the numericals. Okay. So I'm sure all of you can capture this in your memory. Anyway, don't put too much pressure to by heart. So we will be entering into your favorite zone. What is your favorite zone? Numerical problems. Okay. So here we go. See, the first numerical that has been listed here is typically like this. So an electron is orbiting in a circular orbit of radius r under the influence of constant magnetic field. So you see, still I have not yet covered this particular topic of magnetic field, a charged particle moving in a magnetic field. There is something called as Lorentz force. Okay, so if you have heard of that force, F is equal to Q V bar cross B bar. Okay, I'm sure we have not yet done that. So therefore, I will not be able to solve this numerical because I have yet to teach that. So I'm just opening this numerical to give you a glimpse of that the problems, the real problems, the real examination questions will consist of concepts from different chapters. Okay, so I can handle this only after I have taught you magnetism and electricity. Clear? Or anybody knows what is Lorentz force? Just now I mentioned. Okay. Hello, good evening everybody.
Good evening. Good evening.
Okay, fine. Good evening. All of you scream and be happy. Okay, now this is another function, another numerical, wherein we have to discuss something called as work function. The light discharge tube, so and so, etc. The kinetic energy of the fastest photoelectrons. So still photoelectricity is to be taught and work function is to be taught. So therefore this numerical also cannot be worked out. So again, I know you can solve because it is covered in your college. Okay, but it is not yet covered here. So therefore I'll just keep it because I want you to get the theory correct. Okay, so therefore I'm just keeping it pending. So I'm just telling you that all these numericals, they are multi-conceptual numericals. Alright, so well, we can solve this numerical. A single electron orbits around a stationary nucleus of charge plus ZE, where Z is a constant and E is the magnitude of the electron charge. It requires 47.2 electron volts to excite the electron from second Bohr orbit to third Bohr orbit. Find the value of Z, find the energy required to excite it from n is equal to 3 to 4, find the wavelength of radiation from the first Bohr orbit to infinity, find the kinetic energy and potential energy, angular momentum of the electron in the first Bohr orbit. So whatever formula we have derived in the previous class, all of them will be handy to handle this problem. And I have explained what is electron volt, etc. And for your kind information, you can see here that a particle, electron, can be treated like a particle, and this is how it is represented. Of course, you don't have to write blue color at all. And the energy possessed by this particle is E is equal to mc square. I suppose you have come across this term, E is equal to mc square.
Yes, sir.
What does that mean?
Yes,
what does that mean?
Einstein's law of mass energy equivalence, sir, where m is mass and c is the speed of light, sir.
What does it indicate? What does it mean, man? See, when I ask a question, Mr. Ligade, you try to understand. See, everybody can tell E is equal to mc square means product of mass and c square. That is evident. That is visually evident. But what do you mean by that? What is that? What information does it conveys?
Energy and mass are interconvertible.
Okay, I agree. Point number 1. Next. Come on, continue. Everybody can answer this. What do you understand from this? Hello?
Yes, sir.
Yes. Try and answer. Fine. So here you see what it means is, supposing you have an entity of mass m. Supposing you have an entity of mass m, and if you convert all that mass to energy, right, then the amount of energy that the mass contains is simply the product of m into c square. Okay, supposing you have got 1 kg mass, then how much energy will you get? So 1 kg into c, what is the value of c? 3 into 10 to the power of 8. So 1 into 9 into 10 to the power of 16 joules of energy is generated from just 1 kg of mass. You can understand. Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Enormous energy, right? So now you can see that one atomic mass unit, you know, one atomic mass unit,
Yes, sir.
that itself, if you convert, if you take 1 AMU, and if that one atomic mass unit of energy is mass is converted to energy, that itself also becomes enormous. You can see that is the potential of the nuclear energy. So that is the meaning of this. That means any mass, its equivalent is energy. Or if you have so much energy, then if you divide it by c square, then it is equivalent to its mass. That's the meaning of this. Anyway, more to it when I teach you the Einstein theory. There is a small section in your syllabus. Now this particle, this is with reference to electron. Electron can be treated like a particle or as a wave. And close to it there is another concept called photon. So photon is basically electromagnetic radiation. You can see the representation of photon like this. So it is a wave structure like this, and at the end you have got a arrowhead. Can you all see this? Hello?
Yes, sir.
Yes. And this is called one packet of energy. What is it called? This is representing what? One packet of energy. And how much energy is present here? Now this packet of energy, see, electromagnetic waves means it is one of the characteristic of the wave is frequency. So if you multiply the frequency of the photon by h, then you will get the energy possessed by the packet of energy. Got it?
Yes, sir.
Yes, sir.
H. Okay. So now shall we attack this problem? Would you like to solve this? First part I think all of you can solve. A part all of you solve. So the single electron, so ZE, Z is the constant and E is the magnitude of the electric charge. It requires 47.2 volts to excite from first the electron from second Bohr orbit to third. Okay, so I'm sure what have they given here? 47.2. What is it? What is the physical variable here? 47.2.
Electron.
Hey, I didn't ask you the unit. So 47.2. I didn't ask you the unit. What is it physically? What is it? What is it? A physical variable.
The energy provided.
Energy provided, right? So a photon will provide energy. So you see, 47.2 is the energy of a photon, which an electron in the second orbit will absorb and then rise to the third orbit. Is it clear?
Yes.
Yes.
So this is the amount of energy. So what I expected you to tell was, this is also representing what? 47.2 electron volt. What is it representing? See, what is it? That's what I wanted. So you see, here is the nucleus. So you try to catch up with me. So it is going from second orbit to third orbit. Okay. So this electron, we are going to give it a photon energy. How much is it now? How much is the energy it is given? 47.2 electron volts. Am I right?
Yes, sir.
So this much energy is given to this electron, and this electron absorbs it, and then it jumps from this orbit to this orbit, 2 to 3. They have given 2 to 3, right? Second orbit to third orbit. Okay, that is precisely. So this is representing delta E, the difference in the energy. Okay?
Yes, sir.
So now, if you can correct the formula, what is delta E? Delta E will be equal to 13.6 electron volts into what? Z square 1 upon N2 square minus N3 square. Correct?
Yes.
This is what is the formulation. So you see here, you should capture what is the physical, what else that they have told. It will jump from second orbit to third orbit. And so this energy is the energy of the photon that is given. This energy is absorbed by this electron and it will jump from third orbit to second orbit to fourth orbit. And so here you see this data is converted into an information. The information is this is going to be equated to a physical variable delta E, and we know from the Bohr theory delta E is given by this formulation. Okay, now new students, you I can't help it, you are absent for the first 3 classes. Anyway, I have made videos, I have uploaded the videos. See students, whatever link I have sent now, that link is now for all the classes which have commenced from 1st of March. So earlier I used to send a link for a class, right? Now you just have to press it, you will get it in sequential order, 1, 2, 3, 4 classes. Okay, so this is the formulation. I'm sure all of you are very good in mathematics. You will handle this, correct? Hello?
Yes.
So what is the answer? So we have to find out g square here, and 1 upon 2 square minus 1 upon 3 square. This is what is it. Okay? Well, did you get the answer? What is earlier?
Yes, sir. Yes.
Fine. Everybody else also got 5?
Yes.
Okay.
Yes,
Now, the important thing is the methodology that you have used to solve this. That is important, right? So, all of you must appreciate that Z will be a integer. Correct? Hello?
Yes.
So, you learn how to do this fast because your examination is speed and accuracy. I repeat, speed and accuracy. So here you see, this is 47.2 and this is 13.6. So if you pull this 13.6 to the left, 47.2 divided by 13.6. Okay, so this is one thing, and so right side will be left with z square. So this will be 9 minus 4 is 5, 4 9s are 36. This is what you get. So here you end up with 47.2 into 36 divided by 13.6 into 5. You got these numbers. Okay? Now, what I would do is approximately 13.6 into 3 point something. Right? And here 5 becomes 7 point something. Hello, are you with me?
Yes, sir. Yes, sir.
Okay, now 3 7s are 21. Hello.
Yes, sir.
And if you take these points, say some point here and multiply it by 7. Say even it is definitely this is more than 3.5. So this 0.5 into 7 will again give you 2.5. That means now this one, if you multiply, this is definitely more than 21, and it can be somewhere close to 20. This approximate multiplication. And since z square is what? Z is a integer, so quickly you can say it is 25. Now what I am trying to tell you here is, you can get the approximate answer like this. Okay, but anyways, you have to be careful, you have to use a calculator and do that, but this is one quick way of verifying whether your answer is right, because sometimes while pressing the calculator we might press the wrong button. So therefore you can just be assured by a quick verification of the answer. Alright, so z square is equal to 25, therefore z will be equal to. I hope all of you understood this.
Yes, sir. Yes, sir.
No female has told yes. Hello, Vaishnavis, Vaibhavis, Purtis. Did you get it? Hello? Hello? Somebody respond there, girls. What happened? They're not there.
Yes, sir.
Hello, in time tomorrow na yavag kalsudde yavag mugsud syllabus nimge. Come on, keep your mic open. Right. This is the first part. Then the second part. Find the energy required to excite the electron from n is equal to 3 to n is equal to 4. So again you have got to use the same formula. Only thing is n is equal to 3 to n is equal to 4. Right? So that means now this is 3 and this is 4. Here 3 and 4. And now that you have found out the value of z is equal to 5. You have to substitute that and then you will get this value. Am I right? Somebody answer there.
Yes.
So you will get again here 13.6 as it is, but this will be 25 into 1 upon 3 square minus 1 upon 4 square. So you have to find out delta E. Just that you have to substitute it. So what is the answer?
Five.
16.5, sir.
16.53. Okay. The answer is 16.53 electron volts.
Yes.
So you have to excite it. You have to a photon. Sorry, not necessarily a photon. Even thermal energy can do that. But the energy that has to be supplied to an electron, which is in the third orbit, and if you want to cause it to jump to the fourth orbit, then you should provide so much amount of energy. Okay, shall I proceed?
Yes, sir.
Then find the wavelength of radiation required to remove the electron. Required to remove the electron from first orbit to infinity. What is this? Seeing part? What
De
is?
Broglie's wavelength we can use, sir.
Pardon?
De Broglie's wavelength, sir, 1 by lambda is equal to RH into 1 by n1 square minus 1 by n2 square.
What is the de Broglie wavelength?
There is not de Broglie wavelength.
ಏನಾದ್ರು ಒಂದು ಹೇಳ್ಬಿಡೋದು.
Sir.
ಏನಾದ್ರು ಒಂದು ಹೇಳ್ಬಿಡೋದು.
So we can find the ionization potential and
This is basically this is the ionization potential. Yesterday I discussed now what is that 13.6 electron volt means. It means if you provide that much energy, then you can push that electron from first orbit to infinity. That is precisely the ionization energy. Correct?
Yes, sir.
Have you defined the ionization energy in chemistry?
Yes.
Yes, can anybody define?
The energy required to remove the outermost loosely bound electron from an isolated gaseous atom.
Excellent. Excellent. Isolated gaseous atom. That is important.
Neutral, sir. Neutral gaseous isolated atom.
Yeah, neutral and the
Sir, like it is not electrically charged. It is not a cation or an anion.
Gentlemen, when you say atom, atom is always neutral.
Yes.
When you say gaseous atom, it automatically means the number of electrons is equal to number of protons. It is neutral. You don't have to neutralize it again. When you use the concept of when you use the concept of atom, then you don't have to specify neutral because atom is always neutral. Is it clear?
Sir, alpha particle we can also define it as helium.
But see, therefore, see. Now, when ionization potential is defined, your friend used the concept of atom and he defined. Okay, and that is the basic definition. That is the basic definition of this. Okay, now having removed the first electron, now if you want to knock off the second electron, then what is the energy? That is a different concept. All right. So now what will you do for this C part? So wavelength of radiation required to remove it. So here you see the the photon here, as I told you, the photon here is having energy delta E, and if what is this energy? This will be equal to h nu. I suppose all of you know this h nu, and h nu is what? hc by lambda.
Yes.
hc by lambda. Got it? Hello.
Yes.
So
Yes.
this value of h is 3.34 into 10 to the power of what? Minus
34.
34. And c value is 3 into, pardon?
Sir, 6.6.
Sorry, 6.6.
Yes, sir,
Sorry, into 3 into 10 to the power of 8. Okay. So what is it that you get here? You get here 6.62 into 3. 3 2s are 6. 3 6 are 18. And carry this is 18 plus 1, 19. 19.86 into so much. Okay. If you take this as 3. But if you take its exact value 2.99 something, then you get something else. Right? So, is anybody knows what is the value of H into C? Hello?
So 19.87 into 10 raised to minus 26.
So, what you get is in joules. If you convert it into electron volts,
Approximately 1.23 into 10 raised to minus 20.
yeah. So, usually we take this value to be what? We take this value to be 12400. Right? 12400. And see, you take this value 12400, okay, and if you take lambda in angstrom, units, then you can write it like this. Hello friends, are you with me? See here, now try to understand. See, please understand this. This is hc by lambda. Okay. Now this delta E, if you express it in electron volts, okay, and if you express lambda in angstrom units, then this value will be 12400. Correct? Hello friends, are you aware about this? I'm asking you, come on.
Yes, sir, it is correct model.
It is there in the model. Okay, so this will be very handy for all the numericals. Keep this in mind. But remember, you have to express delta E in electron volts. See, the examination can create you confusion by giving you this delta E in different units. They can give it in joules, they can give it in ergs. Okay, just to make the question, I will call it as more interesting. Or if they want to give more twist to it. So be aware. You just convert it into electron volts, and the answer that you are going to get for lambda is in angstrom, and then you can write hc in 12400. So now it becomes very simple for us because we need to get the value of lambda here. So lambda will be equal to 12400 divided by delta E. So here the question was, find the wavelength required to remove an electron from first Bohr orbit to infinity. So this one is not difficult. From first Bohr orbit to this. Remember, from first Bohr orbit to infinity. See, if it was hydrogen atom, okay, then if it was only hydrogen atom, H atom, then for this question, the answer would have been find the wavelength of radiation required to remove an electron from first orbit to infinity. If it was hydrogen atom, then the amount of energy that you want to knock out an electron from first Bohr orbit to infinity would be how much? Would be simply 13.6 electron volts.
Yes, sir.
But here when you take hydrogen atom, Z is equal to pi. But in this problem, they have told Z is, we found out that Z is not equal to 1, Z is equal to 5. Okay, so if Z is not equal to 1 and here Z is equal to 5, then this becomes what? This formula is becomes, yes, you will get here delta E is equal to 13.6 into Z square. Okay, into 1 upon N1 square minus 1 upon infinity. 1 upon infinity is 0. And here the N1 will be equal to 1. So this formula simply reduces to 13.6 into Z square. Clear? So therefore, the amount of energy required to knock off the electron from first orbit to infinity will simply be this multiplied by 20. Hello friends, are you with me?
Yes, sir.
See students, see now, see, it is okay, it's nice that you are using formula and solving it and all. I have also used the formula, it's not that I have not used. But the fact of the matter is, the fluency with which you should be able to interpret and use this data, okay, then that will lead to answers quite efficiently, effectively, and more importantly, you will be quite confident when you get the answer, because you are all going to attempt examinations with negative marking. So your approach to the problem should be such that that when you get the answer, you should be very confident to mark the answer. So what is this value going to be? 13.6 into 25.
340.
340. Excellent. So 340 electron volts. So what it means? So if Z value here, Z value is 5, and then if you have an electron in the ground state, then you have to provide 340 electron volts of energy to knock off that electron. That is, take that electron to infinity. Got it?
Yes.
Now the question is, find the wavelength required to remove. That's the question. So that means now this is the energy. So what we have now got is delta E here. Okay. So we have got here delta E. Delta E is equal to so and so. Now the question is wavelength. So wavelength will be equal to 12400 divided by 340. Because 340 is in electron volt, as I told you, this is so and so. So what is the answer that you get here? See, this is delta E will be equal to Hc, or this will be Hc by lambda. So the value of Hc is whatever. What will you get here? 12400 by 340.
Something 36 points.
Hey, 36 per 36 dollar. 36 per
Units are
6.4.
huh? 36.47. Excellent. That's right.
yes, sir.
36.47 angstrom. This is the answer. So that means now, see, the photon energy that is impinging here, that photon, as I told you, is an electromagnetic wave. It is an electromagnetic packet of energy. We call it as packet of energy or electromagnetic wave, and it is characterized by frequency or wavelength, and of course speed, amplitude. Now here you see the wavelength of that photon corresponding to this. If it impinges, then that will automatically carry this much amount of energy, 340 electron volts of energy, and that will cause the electron to move from its ground state to infinity. That is, it is ionized. Got it, friends?
Yes.
Yes, sir.
Yes. Now, well, the D part, find the kinetic energy, potential energy, and angular momentum of the electron in the first orbit. Find the kinetic energy, potential energy, and the electron. So they are asking you to find the kinetic energy, the potential energy, and the angular momentum. So kinetic energy is denoted by K, potential energy is denoted by this, and this is denoted by L. So we have just seen potential energy will be equal to half the kinetic energy. Am I right? Hello?
Yes.
Minus half.
Or twice, ulta.
Sir,
Yes, sir.
that's
That's
the
2 times.
2 times, no?
Yes.
Okay? Or we can use kinetic energy E. This is also the nomenclature, sometimes they use in E. So here the kinetic energy will be, the potential energy will be equal to 2 times E. 2 times E, I am showing you the magnitude. Okay, so this relation you should know. And angular momentum. So you see, angular momentum, if you know, it is mvr. Okay, and what is mv here? mv momentum also. Okay, mvr, right? So angular momentum is mvr. But now, how will you relate angular momentum with the kinetic energy? How will you relate angular momentum with kinetic energy? Because that is the basic postulate of Bohr. Because angular momentum will be equal to nh by 2 pi. I suppose all of you know this basic postulate. So in this case, they are asking you ground state. So n is equal to 1. So this simply will be equal to h by 2 pi. Okay, friends?
Yes, sir. Yes.
So what have we found out now? See, in the previous formulation, see, we have found out the energy, radiation energy to remove the electron from its ground state to infinity. That means the energy of the electron in its ground state here, because we have got here Z is equal to 5, and then we have got the electron. So now, what is the energy of this electron? We found it out to be minus 340 electron volts. See, for hydrogen atom it is 13.6 electron volts because there is only one proton, but there are 5 protons. So therefore, this is it. Hello friends, are you with me?
Yes.
Yes, sir.
So therefore, 340 electron volts happens to be what? The kinetic energy. So the kinetic, see, the total energy will itself be equal to kinetic energy. Correct? Hello?
Yes, sir.
See, yesterday when we took up the theory, we have proved that the total energy of the electron in a given orbit will be equal to kinetic energy, and this kinetic energy will be equal to half the potential energy. That is what we have proved in yesterday's class. Is that clear?
Yes, sir.
Sir, minus half.
Minus. I'm just writing you all the
First
magnitudes.
was expressed.
I'm writing only the magnitudes. Okay.
Yes.
So going by this, the kinetic energy will be 340 electron volts, and the potential energy. What will be the potential energy? The potential energy will be equal to. See here. The most important thing is writing the answer. The kinetic energy will be 340 electron volts plus 340 electron volts. The potential energy is twice the kinetic energy, but this is going to be minus 680 electron volts. Keep this in mind. I suppose all of you are able to interpret this.
Yes.
Hello?
Yes, sir.
Yes, sir.
Right? Then the angular momentum L is equal to h by 2 pi. H by 2 pi. So substitute the value of h and 2 pi, then you will get the angular momentum, that is 6.63 into 10 to the power of minus 34 divided by 2 pi, 2 into 3.14. Okay, so what is the answer you get here?
approx it is 10 raised to minus 30.
Approximately how much? So if you take this one, 2 3s are 6, 6. So it becomes approximately, if you take here, this is 6. So top is 6 here. So 1.10 something like this. You get it. Into 10 to the power of 34. 10 to the power of 34. But it will not be 1.16 because it is 0.14. So 2 into 1.4 will be equal to 6.28. Okay? Right. Anyways, if you do this properly, you are going to get 1.056 into 10 to the power of minus 30. You are going to get this answer. But the question is, what will be the units of this? What will be the unit of this angular momentum? Hello, my dear friends.
Joules
Centimeter square per second.
Joules, centimeter? No.
Joule second.
Joule second. You will get it as Joule second. How did you get it as Joule second? Because you see, delta E is equal to hc by lambda or h nu. Delta E is equal to h nu. Okay. Now here, so therefore, see, what is the unit of nu? Nu, the value of nu is 1 by s or per second. The unit of frequency is per second, isn't it? Per second. And this side you have got joule here. And therefore the unit of h is going to be joule second. Okay, and in this case what happens? The unit of h is joule second, 2 pi is a constant. So the unit of angular momentum in this case has to be joule second. Did you get it?
Yes, sir.
ನೋಡಿ ಇದೆಲ್ಲ ನಾನು ನಿಮಗೆ ಡೀಟೇಲಿಂಗ್ ಕಲಿಸಲಿಕ್ಕೆ because you cannot, if you simply get the answer 1.56, if you don't write the units, then it is absolutely useless in physics and you will get 0 marks for that. So in all these numericals you have to be very cautious with the units, okay, and the examiners can play with this. They will give you different physical quantities in different units, so you should be able to judge and convert them correctly and handle it. Okay? So here you see, having got this, you should write the unit of this is joule second, JS. That's the right answer. Is it okay, friends?
Yes, sir.
Yeah.
So this basic problem we have calculated many aspects connected with the electron in the Bohr model. Shall we go to the next problem?
Yes, sir.
See, it is almost 35 minutes. No, 40 minutes. Okay, one numerical with all this has taken 40 minutes. It's worth it. Attack this problem. This problem is really very interesting. I've chosen this for you wonderful students. A moving hydrogen atom makes a head-on collision with a stationary hydrogen atom. Before collision, both atoms are in the ground state, and after collision, they move together. What is the minimum value of the kinetic energy of the moving hydrogen atom such that one of the atoms reaches one of the excitation states? Study this problem, and if possible, you draw a schematic diagram of this. Visualize and write it. Aram se, yeah? See, new students, you might find it all, tare zameen pe. Okay? Don't get bogged. You go through the previous videos, you will be able to catch up. Somehow, you see, I have tried to tell everyone that the classes will commence from March 1st. And from day one, you should attend. But for some reason, publicity, people keep on trickling. And anyway, there are a lot of students who have inquired, and I have told it is commencing from March 1st, we are doing it, but some of them are feeling, oh, yeah, March 1st, exam mugdila and all. So I told, this is what is the problem. If I don't start on March 1st, then we will not be able to complete the syllabus in time. Then whatever effort we do will not become that fruitful. Okay, anyways, for those of the students who want to join after the examination, you are most welcome. I will not stop you. So whatever portion I have done from 1 to 9, I will teach it later on. That is, later on I will teach you. But those wonderful students who have attended from first, I don't want to deprive you of learning better, learning quickly, learning correctly. Okay, have you drawn a schematic diagram of this situation? So what is the schematic diagram of this situation? There is an atom. It is having some kinetic energy K, right? And it is in motion. It is having kinetic energy means it is in motion. So a moving hydrogen head-on collision is stationary hydrogen atom. So this is moving. There is a stationary hydrogen atom, right? There is a stationary hydrogen. So this is going to go and collide with this. Okay. So that means now this mass is m, this mass is m, mass of the atom, and its velocity is v. Its kinetic energy is k. This is going to go and collide. And then what they have told, after collision, okay, after collision, they move together. After collision, they move together. So as a consequence, what happens? These two will start moving together. So the mass becomes 2m. Hello friends, are you with me?
Yes, sir.
And
yes,
one more condition that they have given here. See, we have solved this type of problems. One ball hitting another, both moving together. Before collision, both atoms are in ground state. You understand? That means the first electron of both the atoms is in the ground state. And after collision, they move together. Okay? Then, what is the minimum value of kinetic energy of the moving hydrogen atom such that one of the atom reaches one of the excitation state? That means now what it's telling. See, these two are hydrogen atom. That is nucleus and electron. Okay, nucleus and electron. Okay. Hello, are you with me, students? Say yes, sir.
Yes, sir.
Yes, sir.
Nucleus and electron. So this is moving with velocity v. This is at rest. This mass is m. This mass is m. This has stuck this electron. Okay, and this is in the first orbit. The second orbit is empty. Now after collision, this goes and collides. What happens? These two will now become. These two will. This first. This one will be like this, and the second atom. Okay, the second atom. What happens to the second atom? In the first atom, the electron is still in the ground state, but in the second atom, the electron has jumped to its next state. That means now hello, are you with me, students?
Yes.
So this had some kinetic energy. Now the combination will have some other kinetic energy K dash. Some other kinetic energy K dash. But what is important here is that this kinetic and we have to assume it is a perfect collision. So what we have to see is that this kinetic energy K has also got to supply the what? Excitation potential plus the total kinetic energy. Did you understand this formulation? This is the kinetic energy of the system. This is the kinetic energy of the system before collision. After collision, this is the kinetic energy of the system plus this energy of the kinetic energy, delta E energy has been utilized to excite the electron from ground state to its next state.
Yes, sir.
Hello, are you with me?
Yes, sir. Yes, sir.
Now, what is the potential of this ground state? You know, it is minus 13.6 electron volts. What is the excitation potential? What is the potential of this state? What is the energy of the next state? Anybody? Any idea?
23.8.
How much?
23.8.
Yes, good, excellent. 23.8. So, what is the difference here? Delta E?
10.2.
Excellent, 10.2 electron volts. So that means now in this formulation, this is going to be 10.2. Okay, and we don't know what is K dash. But we know what is, we have to find out what is K. Did you get the formula, students?
Yes.
Interesting problem. Now, what you have to observe is, we have got in this equation, what have we got in this equation? We have got an equation here where there is K is unknown, we have to find out, and K dash is another variable which I have assumed, but delta E, see we have formulated the problem, and we, by the data that we know what is delta E. But there are two unknowns and only one equation. Do you appreciate that?
Yes.
So we need one more equation. And then only we can solve.
Sir.
Huh?
Sir, what 23.8 is energy of second shift.
Minus 23.8.
Sir. No, sir.
Sir, not by 20.
How much it should be?
3.3 per atom.
Yes, sir, 3.
Minus 3.4.
Yes.
Yes, sir.
It should be less. It should be less. I'm sorry. Okay. I'm very sorry. It should be minus 3.3.
3.3, yes.
3.2. But the difference is going to be 10.2. Sorry, thank you so much. Mr. Dimant, on what basis did you say it is 13.8?
I had calculated the difference between energy.
No, how did you calculate the difference without knowing that number?
Sir, we know that basics are first year it is 13.6 now, sir. So using that formula, sir.
Using that formula you have calculated. Okay, you are miscalculated. Sorry, thanks others for correcting it. Wonderful students. Fine, but the difference is going to be 10.2. Now let's come to this. K is equal to delta E plus K dash. So there are two unknowns and only one equation. So that means you have to get one more equation. Correct? You have to get one more equation. Now in this situation, what is the physics? What else can be related? Energy is conserved. One equation we have got. So this is collision. In collision, we can use one more concept.
Momentum.
Excellent. Momentum can be used. Right? So the momentum of the system before is equal to momentum of the system afterwards. Okay?
Yes.
So using momentum, can you form the next equation?
Final velocity of the system is equal to half of the instant.
See, now momentum, see here it will be handy to connect momentum with kinetic energy. Momentum is mv. Okay, momentum is mv. So if I multiply and divide by v, okay, so I will get here what? mv square by v. Okay, and I multiply and divide by 2. So if you now take this, so this becomes kinetic energy. Correct? So 2 kinetic energy by, sorry, I should multiply and divide by 100. So it is m. So supposing I take the square of it, I get here p square is equal to m into mv square. Okay, p square is equal to m into mv square. So now here I will multiply and divide by 2. Okay, multiply and divide by 2. So this becomes what? 2mk. So therefore, P will be equal to root of 2mk. Got it? The relation between momentum and kinetic energy, man.
Yes, sir.
Got it? So basic relation. So they will be very useful in such type of problems. P is equal to root of 2mk. Okay, I hope all of you got this.
Yes.
So in this case, the collision, in any collision, momentum is conserved. Correct? So therefore, P will be equal to root of 2km, because the other body is at rest. Only one body is moving. But then after hitting, both of them will join and move together. So this becomes what? Root of 2k into 2m. Because both of them are going to collide and move together. Hello friends, are you with me?
Yes, sir.
So therefore now, from this equation, see, can you get the relation between k and k dash? Have I written this correctly here?
They will be different.
Yes. So this should be k dash. This should be k dash, because you see, now I am relating this equation. Now I have to write this equation separately. So for this, it is k dash. It cannot be same, obviously. So now this 2, that 2, this m, that m will get knocked off, and now directly we are going to get the relation here. Root k will be equal to, okay, the roots also can be knocked off, so only k will remain, and here if you knock off the roots, okay, and 1 2 goes, so you will get here 2k dash. Hello friends.
Yes.
So we got the relation between k and k dash, and therefore k dash will be equal to k by 2, and therefore this equation becomes what? K is equal to delta E plus k by 2. This equation will reduce to this. Hello friends, are you with me?
Yes.
So what we have to find out was k. So if you pull this k this side, so this will again become k by 2, and therefore this will become k by 2, and therefore k will be equal to 2 into delta E. Okay, so delta E we found out to be 10.2, so into 2 becomes what? 20.4. 20.4 electron volts. What is this? This will be the kinetic energy of the first hydrogen atom which is in motion, and if this collides with the stationary hydrogen atom, then both of them will move together with the new kinetic energy k dash, but one of the electrons will get excited. Got it, friends?
Yes.
See, again, you can see what are all the concepts that you have studied in first year mechanics. The collision theory, right? And in the collision theory, you are using momentum, you are using kinetic energy, and now you see how it is getting applied. So as we proceed in the second year, and if I am choosing those problems which is okay, these problems were asked in some examination. So now you can appreciate that why I am insisting that all the 30 chapters must be completed. If first year 15 chapters, second year 30 chapters, all are completed, then the numericals that we are going to do in the month of December 2022 for the examination, you are going to write in January end or February 1st week 2023. The numericals will be multi-conceptual. It can be a mixture of any topic or topics of first year and second year, and as I told you, the first year mechanics will be continuously used in the problems that we solve. Now you see atomic structure. In this only you see electricity, magnetism, collision, so many concepts are being used. I suppose you at least now appreciate why I am insisting. Let's try and complete the second year topics at the earliest, so then we can solve the real problems. Now solving chapter wise problems is not going to help you at all. It is not at all going to help you. It is okay, you have to understand the concept, so few problems can be solved. but the real problems will be after you complete the entire syllabus. So therefore, we have to find sufficient time after the completion of syllabus so that we can practice the real type of problems. That is why very good education centers for these type of examination, they will complete the first year, second year syllabus as early as July, latest by August 2022, so that you can be well prepared for the examinations of January 2023. And all of you can do it. If many can do it, you can also do it. It's only that you have to have faith and confidence in me and say, yes sir, you tell, we will do. And you will inch towards that point. Okay, at this stage, you might feel, oh, how is it possible and all. But I have seen many times it is possible. Okay, and it is up to you to make it possible. Alright, shall we go to the next problem?
Yes.
Yes.
What next time? It is already 9:45. Okay, fine. No issues, no issues, huh? No issues. It's both the problems that I have chosen is wonderful problems. You will learn a lot from this. Okay, friends. 1 minute.